Great. Well, I wanted to just describe some of the platform technology that we've developed in my group that could be used for regenerative medicine and also as anti-fouling surfaces. And these are using collagen-based peptides as biomaterials. So I just want to take you through a little bit of the science that goes behind it and show you some of the results that we've gotten that could be useful for these two applications. We've designed peptides based on collagen. Collagen, of course, is very useful for tissue engineering, but it's very difficult to control the morphology of its structure and also the chemistry that it's displaying. So by simply synthesizing small peptides based on collagen that can form triple helical structures, we can introduce within these structures assembly signals that can allow for hierarchical assembly into three-dimensional structures. So for instance, depending on where we put the assembly signals, we could, if they're at the ends, get to a linear type of a design of long structures. If we put these self-assembly signals in the center, we can get to radial designs, or if we put them both at the ends and the middle, we could get to highly cross-linked designs. And in this case, what I'm using for the self-assembly signals in this particular application are metal-ligand interactions to get the hierarchical assembly. For instance, if we're looking at regenerative medicine, we can use the linear-based assembly to make these highly ruffled microflorette structures that are at the micron level that we can decorate either on the interior or on the exterior with a variety of different biopolymers, including growth factors. And interestingly, because of the nanoscale morphology on the surface of these materials, they have a very good affinity for cell binding. So for instance, here's an image of these microflorettes interacting with a stem cell. And so we'd like to use these as stem cell delivery vehicles whereby we can have a temporal release of different biopolymers, such as growth factors. In the radial design, if we have our metal-ligand interactions in the center, we can get this small collagen peptide to further assemble into hollow cages. And these hollow cages we can decorate either on the outside through chemistry or the inside through encapsulation as drug delivery vehicles. And if we have our ligands for the metals either at both the inside and the exterior, we can get to highly cross-linked materials. Here you're looking at a three-dimensional matrix that is highly cross-linked and has pores that are available for cells to be able to be encapsulated and grow. In addition, we can also start to grow tissue within these materials. And we've been looking at this for cell and tissue growth and also for wound healing applications. So a single peptide, by the way in which you decorate it, can allow you access to all this multitude of different structures. And since they're held together by metal-ligand interactions, one can use a light treatment of chelators for the metals and also release any of the encapsulated materials, cells, or tissue that are entrapped within these materials. In addition, we've been looking at these for anti-fouling surfaces. We've been looking at our inspiration, the lotus effect, where you have nanoscale and microscale patterning and hydrophobic surfaces that are available. I just showed you with the microflorettes and the highly cross-linked structures that we have that nano to micro size topologies. But we also have some other structures where we have a microscale hierarchical assembly when you can see the nanoscale patterning that's based on the way in which these materials are assembling. And we can, since I know every 10 nanometers what chemical functionality is right there or right there within the materials, we can modify them with a range of different hydrophobic or lipophilic groups that can allow us to get into anti-fouling types of surfaces that could be used for implantable devices, for instance.